Right, today I want to start by kind of building off what we did in class before with our the applets kind of on page 6. I'm going to start on page 7. Now we did fill in this top part up here before. So if let's just remember kind of what we talked about before. The mean of a sampling distribution. Now remember I'm talking about a sampling distribution, not a sample distribution. A sampling distribution meaning I take a bunch of samples, I find the whatever I'm looking for, the proportion in this case, and I plot those on the graph. So we take a bunch of p hats and we plot them on our graph. We'll get to means later. This time we're talking about proportions. So we'll worry about means. It'll come up next after we're done with the things we do today. But for now, we're going to focus on proportions. So if I want to find the mean of my sampling distribution, the sampling distribution meaning where I took a bunch of sample proportions and I plotted them on the graph, the mean should be around p, which is the true proportion of the entire population. Then I'm looking for maybe the standard deviation of my sampling distribution. And we can use this formula here that we've written on that here before. Again, this is assuming either independence or that the 10% rule is satisfied. And then we also said that we can assume that this sampling distribution is approximately normal if it meets the large counts condition that we talked about back in the last chapter, and then the large counts condition I've written for you down there below as well. So let's go ahead and put the date. Maybe I have a little squiggle black line where I want you to put the date. And let's talk about some more notation. And specifically today, I want to get into when we have two different either populations or treatments. So in this case, I would be looking at two different graphs, two different sampling distributions. And I want to make some comparisons between the two. So maybe I have two different populations that I'm taking information from. That's what we're going to look at in example 7. Or it's possible that we're running an experiment. We have some people that are taking the control and some people that are taking the actual thing that we're looking for, whether that be a drug trial or whatever it is. So maybe when we want to make a comparison between how people in the control respond versus how people who are receiving the actual treatment respond. So I'm just going to call them 1 and 2 for now, so we can differentiate the first population, the second population. They'll each have their own parameter. So something will be true about the entire population, and that would be P1. If I was able to sample everyone in the population or everyone who received that treatment, I could find the true proportion, P1, and the true proportion, P2. Well, then I'm going to have the statistic P1 hat and P2 hat. So if I take a sample from my first population, I would get P1 hat. If I take a sample from my second population, that would be a sample proportion P2 hat. And then I also potentially have two different sample sizes. So now I need to differentiate between the two different sample sizes in 1 and in 2. Let's take a second to read example 7. So I'll give you a minute to kind of look through it here. And if you want to pause the video now and you can read through it. Mr. Urban wants us to run some stats on FHS and HSC to confirm what he already knows. Fisher's is far better. So we have some information here about Fisher students and HSC students. Now the 70%, this is my P1. That is of everybody at Fisher's High School. I believe that 70% of them did their homework last night. That's P1. This is going to be P2, the actual proportion of students at HSC who did their homework. But Mr. Swaim is only going to take an SRS of 100 students. Since this is a sample, we'd be looking at P1 hat. And Mr. Fletcher, who's an HSC counselor, he's going to take another SRS, and this one is of 200 students. He's recording the proportion, P2 hat, who did their homework. So they're just taking a small sample of everybody at either FHS or HSC, and those would be our sample proportions, these statistics that have hats on them. And so what I want to do is I want to make some comparison between P1 hat and P2 hat. So what I did is I used software to take an SRS of 100 students. Now this is from the first population, N1. So N1 is going to be 100. N2 is going to be 200. HSC is my second population. So I'm going to plot all of the values of my P1 hats, my P2 hats, and then I took P1 minus P2 hat. So let's kind of talk through how I did this down here. Here's the graphs. So these are the sampling distributions of P1, P2, and then the difference of P1 minus P2. So let's say, for example, and this is just an example here. Let's say that in the first distribution, so Mr. Swaim taking the SRS of Fisher's High School students, he found that P1 hat was 0.68, close to the 70%, but maybe not exactly close to exactly the 70%. And then Mr. Fletcher did the same thing, And in his sampling distribution, he got a P2 hat of 0.505. Again, close to the 50% that we expect, but not exactly that due to just the sampling variability there. So then what I did to find the sampling distribution was I took each outcome from both of the two counselors, and I took P1 hat minus P2 hat equal to 0.68 minus 0.505, and that gave me a value of 0.175. So one of these values here at approximately 0.175, that would be this value in this example. Okay, that's kind of how I found this value. So this is going to be the difference and taking many, many, many samples. Okay, so let's take a look at what we see. Think about the shape, center, and the spread, because I am going to ask you to describe those distributions on the next page. And so you can think about what kind of shape is it? Do they look approximately normal? Where do you think the mean of these dot plots are? And then we're going to talk about that on the next page. So first things first, let's recall what we talked about before. And so I did put a little box around this. This is kind of what we talked about on the last page. The shape is approximately normal if n and p are greater than or equal to 10, and if n times 1 minus p is greater than or equal to 10. There's the formulas for center and spread. And so what I'm going to ask you to do is to describe the shape, the center, and the spread of just P1 hat and P2 hat. So we can take exactly what we talked about before, and we're just applying it twice to both of these two sampling distributions. So you might have to switch back and forth a little bit between your two pages. And actually what I'll do is I will leave the picture up here for you guys to take a look so you have access to all the data up above. You have access to the graphs if you want to pause the video, and then you can describe these two distributions, just shape, center, and spread. Let's not worry about unusual features today. Alrighty, so what I have shared for you here is what I would say for shape, center, and spread for both of the two sampling distributions here. We found the center to be their corresponding true proportions. And I want to take a second to look back here. I said that the true proportion of Fishers High School students that we think did their homework last night is 0.7. Well, that looks pretty close to 0.7 around here. And we think that for P2, we think that's about 0.5. I mean, these are right there in the middle of our sampling distribution. That's really good news. And so when I'm looking at the potential for how much better do Fishers High School students do over HSE students, I want to look kind of somewhere in the middle over here. And wouldn't you know it, it looks to be about 0.2. You see how this is, it's kind of hard to see. I know the picture is not great quality, but it is the height. And if that loaded there, you'd see the height was about 0.2, which isn't that equal to 0.7 minus 0.5? Interesting. And maybe we'd want to also figure out the standard deviation. Now, the standard deviation is much harder to just estimate from the graph. So let's see if maybe we can apply what we learned about random variables to this situation as well. So when we were combining random variables, we could find a sigma of two different random variables combined. So in this case, I want to take P1 and P2 hat. And if you remember what we did before, we squared the standard deviations to have variances. We added the variances together, and then we took a standard deviation at the end. Well, if I square the formula for the standard deviation, that just gets rid of the square root. So I could square it, and in this case, I would have 0.7 times 0.3. And then that's divided by n1 of 100. And if I squared the other one, I would have 0.5 times 0.5 over 200. Now this was for the variance, so I do need to take a square root to have a standard deviation. And you can use the values that we calculated above. Let's calculate what this is. This same formula applies to our sampling distributions when we're combining them together. That's pretty cool. It's the same formula. So let's talk about, we have these two sampling distributions. We've now thrown them together. We've made a new sampling distribution. And I did not put a title on here. I should have. This is when we're comparing proportions. Let's talk about the shape, the center, and the spread. Anytime we're taking two sampling distributions and we're throwing them together. So the shape, we can still assume approximate normality. if. Now let's take a look back here. This graph, the sampling distribution of the P1 hat minus P2 hat looks pretty normal to me. I mean, it's going to have some variability, but it looks not bad. It's definitely not skewed, so that's good news. And so we can assume approximate normality if things hold true. Well, we need the large counts condition to hold true for both of our two populations. So we need to take N1 times P1, as opposed to N times P. Now I need to specify N1 times P1. That needs to be greater than or equal to 10. I also need to have N1 times 1 minus P1 greater than or equal to 10. That would be for the first P hat. So now we need to do the same thing for the second P hat. N2 times P2 needs to be greater than or equal to 10. And N2 times 1 minus P2 needs to be greater than or equal to 10. So we have to check 4 things here since we've got the 2 populations, and for each of the 2 populations, we need to check 2 different things. So we have a lot to do, but it's nothing that's super crazy or something that's super new. It's just we have to check them for now both of our populations. In order to find my center, this would be mu of P1 hat minus P2 hat. And all we have to do is take P1 minus P2. We took 0.7 minus 0.5 up above. We got approximately 0.2 as my center. This will work for this one as well. For the spread, I need to check the I need to check the 10% rule, or I need to have independence. So we need to first check, why does it do that? A and D, C, check independence or the 10% rule. And if we check the 10% rule, we need to check it for both of our populations. So N1 has to be less than or equal to 1/10 of capital N1 being the entire population for my first population, the entire population size. And then the same thing for N2 with my second population. So again, it's just kind of twice the work because we have this, in this case, 2 populations as opposed to 1 population like we've had in the past. And if this is the case, we can find the standard deviation of P1 hat minus P2 hat equal to a big boy square root of P1 times 1 minus P1 over N1 plus P2 times 1 minus P2 over N2. And I did put the little squiggle line around this because I should have bolded this. These are going to be the formulas that we're going to want to use kind of moving forward whenever we're comparing 2 proportions.